2, 1. Alright, let's go. We're almost done. We're almost there. One more tool before we start making integrals. So, last time we set up this idea of simple functions, which we noted kind of look a little bit like Riemann sums, but the pieces, the underlying sets, they may not be intervals. And so in order to properly compute that area, we need some sort of notion of length. That's where measures come in. All right. Now let's jump right into it. What are they? Okay. So, a couple things to digest here. So the big one is, the equation is staring at you. The idea here is that a measure is going to be a thing where when I look at the measure of a union, it's going to be the infinite sum of the measures of the individual pieces, but we want some ground rules here to make our lives not a nightmare. So obviously the union part of it, the constituent parts, we want them to all be disjoint, so there's no overlap, no double counting. Okay, and I want to throw in a couple of things here. So obviously we want these to be unmeasurable sets, which we kind of already noted are the sets we want to be working with because they give us measurable functions, and they are the things that behave well with pointwise convergence, as we've thoroughly vetted at this point. So, makes sense with all of that. Now, the only thing I want to throw in here is some adjectives. I'm just going to use the word measure for this thing, but I do want to note that, first of all, non-negative, so these are usually referred to as positive. And I will also throw in that I'm only going to work with finite measures. You can work with infinite measures that allow for the extended real number infinity, but I personally have always hated that, and I feel like it just makes everything super clunky because you always have to do an exceptional, what happens when one of these sets is infinite. And again, when it comes to the traditional Riemann integral, we're always working on a bounded interval, so yeah, you can make this a little bit more robust than what I'm gonna do, but I like being finite and positive. I don't know about you. Okay, so now that we know what they are, let's prove some basic things about them. Alright, and we got two propositions that give us a bit more of a feel of how these things work and some things that we're going to use with them, and they are as follows. So, first we'll prove that the empty set indeed will always have measure 0. Makes sense. Okay, for disjoint sets, the same thing holds, so finite, it will still carry over, even though the assumption started with infinite. Alright, then we'll prove a set difference. This right here, you're not going to believe what we can do with this. So we'll prove this set difference property. We'll also demonstrate monotidicity, very useful. And then we'll point out that a union doesn't necessarily need to be disjoint in order for the measure to say something. The thing is that we don't have equality. What we rather have is something that's usually referred to as subadditivity. All right. Okay, so those are the four things we're going to prove, so let's prove them. All right, first one's super easy. Countable collection of measurable sets, all of them are the empty set. These are trivially disjoint, and pop the empty set into all of it, you get this. Alright, the only way I infinitely added something up and got back to where I started is if I had 0. There's no other real number positive that does this. We're good. Great. We send 0 to 0. The way we like it. Alright, and then equipped with that, if we've got a disjoint finite collection, then I can just throw on as many empty sets as I want to get to countably infinite, and then we just prove that the measure of the empty set is indeed empty. The union, note, will only count the first n things, because after that I'm thrown on the empty set so nothing happens. And there you go. Sweet. Alright. Now, following that, equipped with that, I can prove the following. Note that any set can be written as this union, because B is equal to the stuff that's in B that is either in A or not in A, because you're either in a set or you're not in one. And note, the intersection of these two is empty, so B here can be written as this disjoint union. So by my previous point, I know that the measure of B has to coincide with this measure, which can be split additively like that. And then we simply subtract n. Hey, there we go. Now, note here that this is a non-negative thing, so this has to be non-negative, meaning that the measure of A is less than or equal to the measure of B. Cool. So there's the monotidicity. Alright, now let's prove that if I do the measure of a finite union, it's going to behave the way we want it to. Note that any union can be written as a disjoint union as follows. The things that are in A and B are the things that are either in A, not in B, not in A, or in their intersection. Alright, so the measure then splits across, because this is a disjoint. Note that this is a non-negative thing, so multiplying it by 2 only makes it bigger. And now if I group these together, you may recognize that, hey, that union with that will simply give me A. And we kind of already made this little move up here, and indeed, here and here will get us that. Alright, pretty cool. Sweet. Okay, cool. So we've proven some basic things about measures now. Let's prove some more advanced things about measures, and this will be the next 3 points. And these are going to be very powerful tools for us, because this is going to let us basically pass limits with measures. So, specifically, if I have a sequence of measurable sets that's monotonically increasing, alright, well then the measure of the union is precisely the limit of the union of the measures of the individual things that are unioning up to it. Alright, I note that the sequence is in fact monotone, but the monotone is essentially for free because we've already demonstrated measures are monotone themselves. So, alright. And likewise, if we have a collection of sets that is slowly decreasing, and if I look at their intersection, the limit passes there as well. So here we see there's kind of a continuity that I can do with measures. I can pull limits in accordingly with intersections and unions. And something we're going to make use of is that while the measure of a countable union is equal in the disjoint case, in the non-disjoint case, we know we can bound it above so long as this thing is convergent. And that's a lot of times, as you'll see, a lot of the tricks here in the measure world is going to be, can I bound this stuff above? And if I can, then I can get away with some stuff. And we kind of saw that with sequences in general. If you can bound things, then we can, there's some tricks we can pull. Alright, so point 1 is really the heavy hitter here. The other ones are basically once you got one, you got the others. So let's see how 1 goes down. And the trick is, of course, I need to get things to be disjoint because measures like disjoint things. So I'll create a collection of sets as follows. I'll start with the initial set, and then the next set will be the next set in the list, but delete the previous one. So in other words here, I'm going to create the union, but I'm going to disjointify it. So indeed, note if I union up A1 to AN, I'm just going to end up with EN because, note, if I union all of these up, I'm just going to collect all the stuff up to EN. Right? Because here, this union will pick up E2, but then E2 will get subsumed in the next one, and the next one, and I'll just end up with EN at the end. Alright. And furthermore, note that these ANs are going to be disjoint from each other because the ENs are monotonically increasing. So here's a technical explanation for it, but right, intuitively, that makes sense because I'm looking at this union that's inflating up to the set E, and at each stage I'm throwing out the previous things, so each one of those ANs are going to be disjoint from each other. So these ANs are disjoint and they have the same union, so that means the measure of EN would be, note the measure of these things, and these are nice and disjoint, so the finite union pulls apart. But we know that E in the end is equal to the union of all of this, which will give me this, the infinite sum like that, and hey, taking the limit, that's the limit of the partial sums. Hey, it lines up, we're good, I'm happy, we're great. Okay, and like I said, this is going to be a pretty powerful tool. We're going to use this once we start building up integrals, but there we go. Okay, now point 2 is basically, hey, just start doing the complements now, because instead of going monotonically up to the union, well, I want to monotonically go down to the intersection. Well, we know unions and intersections are connected via set differences, so let's just let Bn be the first set, but delete the nth set you're at. Okay? Then now, these are going to be monotonically increasing, right, because these are monotonically decreasing, so if I complement them like this, I'll get a monotonically increasing sequence. So by point 1, the limits work out the way we want them to. Alright. But now, let's note that the BNs, right, if I look at the measure of these, that's just the difference, like that. And now when I take a limit across the board, as we'll do in a moment, things are going to work out. Because now if I look at B, well, B, which is the union of all of these, will be this union by De Morgan's. I could pull it out, and hey, I've got this complement, so now I've got this, and alright, yep, just hit it with some limits, and it all cancels out and gets you what you want. Alright. Right, so as I noted, right, we're doing, point one was the monotonically increasing up to the union, point two is the monotonically decreasing down to the intersection, but we know unions and intersections are connected via complements, as we see here, so it all worked out. Great. Alright, now for the final point, what happens if we have a union that is not disjoint? Well, if we let AN be the union up to the nth step, what do we know? Well, first of all, hey, note, this would give you a monotonically increasing sequence, right? Because you're just adding on to the sets at each stage, so they're only getting progressively bigger. So point one tells me that the limit of these will line up accordingly to that. Note the union of all of the ANs has to be the union of all the ENs, because it's just, yeah, we're good. Okay, but now let's look at the measure of each one of these. Well, we know that those are going to be less than or equal to, as we proved, the subadditivity in the event the sets you're working with are not disjoint. If you look at their unions, you only can get less than or equal to. But of course, obviously, we're adding up non-negative things, so any partial sum is less than or equal to the infinite sum. All right, and there you go. Now we know the limit of this is not going to exceed that, and life is good. All right, there we go. Cool. All right, so last time we talked Borel, so naturally we want to talk about measures on Borel sigma algebras, and we'll call those Borel measures. Okay. And again, if I wanted to be super precise, I would say a finite positive Borel measure, because again, I'm very particular about my measures. Okay. Now, obviously, once you've got a measure hanging out with the Borel sets, we really want to know what the measure does with open sets. But note the countable additivity thing, this measure of the union equaling the infinite sum of the measures. There's absolutely nothing in there that tells me anything about open sets. So if I'm going to look at Borel measures, I'm going to have to throw in another condition to tell me how is it going to interact with the open and closed sets. And the word that's thrown around is regular, and regular is not a standard term here for what I have listed here. If you Google regular Borel measure, you're not going to get this. But I was taught that this is what a regular Borel measure is, so this is what it is, damn it. Anyway, so what is it? Well, we'll say a measure is regular if the measure of a set has something to do with the open sets, and vice versa, it has something to do with the closed sets, right? These are on the Borel sets, so they have to be related to the intersection of X with open sets. And in particular, we'll say we're regular if the measure is the infimum of the measure of all of the open sets who contain E, basically. All the So, right, that makes sense if we're thinking about a set and you're covering it with open sets, hey, open covers, and then we want to look at the measure of those and, crunch down. Go collapse the open set down on top and see what we get. And similarly for the open set, the same thing for the closed set, inflate the closed sets up on the inside and see what you end up with. Right. And because if we're going to declare regular to be this with infimums and supes, that means there's going to be an epsilon characterization. We like epsilons. All right, so it turns out to be regular means that any Borel set given an epsilon, there is an open set U, so that the set difference of E with the relative open set does not exceed epsilon, and similarly with the closed set, E deleting this relative closed set also has measure strictly less than epsilon. So in other words, the open sets and the closed sets, we can use them to roughly approximate what the measure of a set needs to be. So if I have a good handle of what the measure of open sets and the measure of closed sets are doing, then I basically know what the measure is doing. Okay, makes sense. All right, and this proof doesn't really have a lot going on, so I'll kind of fly through it quick so we can get to the big punchline proof for this video. Right, so take a Borel set, let epsilon be given. Okay, well, for regular, that means that the measure of E is the infimum. So if I hit it with an epsilon, it's no longer the greatest lower bound, so there's something less than it. Okay. All right, similarly with the closed set, if I pull it back, there is a closed set whose measure is bigger than it. All right, and then, as I noted, if you've got nice subsets going on, then set differences behave nicely with measures. All right. And there you go, that's it. So that was the forward direction of the proof, and the reverse direction is essentially exactly the exact same thing. because given a Borel set, given an epsilon, I want to show a regular. Alright, well, we know this is clearly a lower bound for the set. Now I want to show it's the infimum. Alright, well, given an epsilon, there is an open set, so this happens, but we know what the measure of this is. It's this difference, so you just add that over, and hey, there you go. It's essentially just reworking what we just did. And, yeah, good stuff. So, like I said, that one really isn't anything too crazy, but it gives us a nice epsilon characterization for these regular Borel measures. Okay. Alright, now for the star of today's show. Now we've got measures under our belt and Borel measures, let's talk about sets of measure 0. Because it turns out that this is going to be a very helpful thing. Because a lot of times we can't get things precise, but we can kind of throw out sets that have measure 0. Like, oh, I don't know, like the rational numbers or something, you know, like maybe I had a function that was a 1 on the irrationals and 0s elsewhere, and man, it'd be great if I could just ignore what's going on the rationals and focus on the irrationals. Anyway. Okay, so, let's be a little more precise with this. So the phrase that's thrown around is the word almost everywhere. And broadly speaking, this is if I have a sigma algebra and a measure, we'll say something holds almost everywhere if there's some measurable set with measure 0, and the property is true off of that set. Maybe relative to another, or something like that. We'll see an explicit example in a moment so you get a flavor for it. But it's worth noting that almost everywhere is abbreviated as, I'm missing some quotations there, it is abbreviated as A dot E. So AE. Almost everywhere. Unless you're looking at other sources, and some people will do PP, which is French for Parisque Partout, if I remember that correctly, which is like the French for almost everywhere. So certain math sources will use PP to mean almost everywhere, but AE almost everywhere is pretty standard. Okay. So, let's finish up today with a neat little thing, which reveals now that Borel sets, as you may have suspected, probably really only involve countable intersections or countable unions of open or closed sets. And if you remember, we call those things a G delta for a countable intersection of an open set, and an F sigma, which is a countable union. Well, it turns out that if you're looking at a regular Borel measure, of which the Lebesgue measure, which we'll hopefully touch on in the next video, or next, not that video, maybe the one after that. Right, because we're doing things abstractly. We're going to go concrete later on. Hopefully, time permitting. So if you've got a regular Borel measure, then being a Borel measure means that you're a G delta set almost everywhere. Right, so meaning that you were equal to x intersected with a G delta, except off of a set measure 0. So you're not exactly equal to it, but there's some set with measure 0 where, off of it, you're good. Alright, so let's see a proof of this so you get a better feel for what almost everywhere really means. Okay, so suppose that you are Borel measurable. Well, then we can find open sets UN, so that E is contained in the relative open set, and the measure of the set difference of them is less than 1 over n. Alright, let G be the intersection of these, so note G here is in fact a G delta, and let's let Z be the set right here. So, the things that are in this intersection but not in E. So G is a G delta. Furthermore, note that E itself is this set minus that set, right? Because if you're in E, then either you're in this or you're not in that. And if you're not in that, right, so sorry. Alright. So, yeah, if you're in this set, you're either in E or you're not in E. Okay, and if you're in E, then you're in E. But if you're not in E, then you're in Z here. So if you're not in Z, then you have to be in E. Alright. So now if I look at the measure of this set, note, specifically now if I look at the measure of the set Z here, alright, that's equal to this. But we know that each one of these is contained in one of those. So this is always less than or equal to that by the monotonicity. and each one of these was chosen, so we're less than 1 over n. So this set Z here, in fact, has measure 0. And since this set Z is measure 0, that means that E is basically equal to the set, except for the set of measure 0 where, yeah, some stuff's going on over there. Right. So, there we go, right? We proved that E is, in fact, equal to this, except there's some junk hanging out here, but this measure, that's 0, so I don't care. Okay. There we go. And we'll see almost everywhere being a powerful tool when it comes to integrals in the next video.